So far we have seen that two area interconnected power system. Now we will see few more examples. These examples are quite easy one, because we are not carrying out any simulation or anything. So see this, I have made it example A, B, C, D like this. So after that I will tell you something more. So a 100 megawatt generator is operating onto an infinite network, right? So the regulation parameter R is 3%. By how much will the turbine power increase if the frequency drops to 0.20 hertz with reference that your what you call the reference unchanged, right? So system frequency is 50 hertz. So now it is actually 3%, that regulation parameter is 3%, right? That is R is 3%, means that power will increase 100 megawatt for a 0.03 per unit or 1 hertz drop in frequency, because it is a 50 hertz, right? So 3% of 50 hertz means 1.5 hertz, right? So it is understandable, the 3% of 50 hertz is 1.5. So R will be 1.5 upon 100, so 0.015 hertz per megawatt, not per unit megawatt, because it is 100 megawatt, right? It is hertz per, we are not converting anywhere in per unit, it is hertz per megawatt. Now it is given that frequency drops 0.20 hertz, that is delta F is equal to minus 0.20. We know this formula, delta PGSS is equal to minus delta F steady state by R is equal to minus of this drop is actually it is drop, not increase. That means it will be minus 0.2, right? That's why this is minus of minus 0.2, and R you have got 0.015, right? Therefore it is 13.33 megawatt, right? So this is the what you call, this is the answer, 13.33 megawatt. So this example are not difficult one, simple one, only little bit understanding is required. Now look at this example. It is also a small example, but so many things are written. It is example B. It is example B, right? Two generators of the ratings 40 megawatt and 400 megawatt. That means rating of one is 10 times more than the other one, 40 megawatt and 400 megawatt respectively, are supplying power to a system. The frequency is 50 hertz. That is operating frequency or nominal frequency of the system is 50 hertz, and each generator is half loaded. That means 50% of that is loaded, half loaded. The system load increases by 110 megawatt. So all of a sudden system load increase to 110 megawatt, and as a result the frequency drops to 49.5 hertz. That means actually frequency was your 50 hertz, now operating frequency is 49.5 hertz. That means delta F actually, that drop actually minus 0.5 hertz, right? What must be the individual regulation if the two generators should increase their turbine power in proportion to their rating, right? So whatever that means you have to find out R1 and R2. Look, two generators should pick up 10 megawatt and 100 megawatt respectively, because look, one rating, this rating is 10 times more, right? 10 times more, and load increase is 110 megawatt. So if one the smallest one, if, and it was still mentioned that 50% loaded, that means this generator is 20 megawatt, this generator 200 megawatt is generating. That means it can further generation power. So here it is 110 megawatt, that means 10 megawatt by smallest generator and 100 megawatt by the larger generator in proportion to the rating. That means 10 times more, because this rating is 10 times more. So here also this 110 megawatt can be divided, that 10 megawatt will be picked up by this generator and another 100 megawatt will be picked up by this generator. So total is 100, 10 times more as in proportion to the rating, right? Therefore two generators will pick up 10 megawatt and 100 megawatt respectively. That means smaller one will take 10 and larger one will take 100, 10 times more. Here also it is 10 times more, just in proportion to the rating. So number A, regulation for the smaller unit R1 will be 0.5 upon 10, because the frequency drop actually 0.5 hertz. It is 50 hertz, 49.5 hertz. So 50 minus 49.5, so 0.5 hertz, right? Therefore R1 will be 0.5 by 10, so 0.05 hertz per megawatt. A simple thing. Similarly, regulation for the larger unit R2 will be, frequency drop will remain same, that is 0.5 hertz, but it picked up 100 megawatt. So it will be 0.5 by 100, right? So that will be actually 0.005 hertz per megawatt. So problem is very big, but solution is just in 2 lines. So you have to understand that how things are happening. So R1 it is case 0.05 hertz per megawatt, and this is R2 is equal to 0.005 hertz per megawatt. No question of per unit here, megawatt, it is just megawatt, right? So this is that problem 2. Now another one is, this is, say this is your example C. This is example C, the third example. You have to determine Kp and Tp. That is Kp is, we have told, the power system gain, sometimes we call, and Tp the power system time constant, and D that is sometimes we call that your what you call, that is del PL or del PL upon del F, right? So the load frequency control parameters for a control area having the following data. You have to determine Kp, Tp and D, and these are the parameters given. The total rated area capacity is given 1000 megawatt, right? Inertia constant H is given 5 seconds. Regulation parameter R is given 2 hertz per unit megawatt. Here it is given hertz per unit megawatt. Normal operating load is 500 megawatt at 50 hertz. Assume the change in load 1% for 1% change in frequency. Right, this is the problem. You have to obtain Kp, Tp and D. Now first you have to find out the D. D is equal to del PL upon del F divided by the rated capacity. Then D will be in per unit, right? So del PL is, just look that your what you call, it is del PL upon del F. For what we are writing, that total area rated capacity 1000 megawatt, and your change in load is 1% for 1% change in frequency. So that total load is 1000 megawatt, right? Total load is 1000 megawatt, and 1% for 1, and your normal operating load is your this capacity, and operating load is 500 megawatt, right? Therefore 1% of 500 actually 5 megawatt. So delta PL actually 5 megawatt. Understandable, not writing, understandable, because your load is 500 megawatt, and your what you call change in 1% load, 1% means it is 5 megawatt. So delta PL is 5 megawatt, right? And your 1% change in frequency is 50 hertz. So 1% will be 0.5 hertz. So that's why this is 5 megawatt change in load divided by 0.5 hertz and divided by whole thing by your 1000, right? So that means 0.01 per unit megawatt per hertz. Actually, if you have any confusion, that operating load actually it was 5 megawatt, right? So 1% of this, 1% of 500 megawatt is equal to 5 megawatt. So your rated capacity, this rated capacity is 1000 megawatt. That means rated capacity is a PR is equal to 1000 megawatt, right? Therefore this 5 megawatt, and if you convert it to the per unit by 1000 megawatt, so that will actually become 005 we call per unit megawatt, right? So that's why we have divided it by 1000, and change in frequency actually your what you call that your 0.5 hertz. So change in frequency is 0.5 hertz. Therefore your D will be 0.005. This is actually your delta PL in per unit, and this is actually your delta F. So delta PL upon delta F, right? This will become 0.01, right, per unit megawatt per hertz. So that is what we have got, that D is equal to 0.01 per unit megawatt per hertz, right? And we know Tp is equal to 2H upon D into F0. F0 is the nominal. I told you that capital F0 or small F0, they are same, right? Sometimes I have made it most of the cases capital F0, but doesn't matter. So operating frequency F0 is 50 hertz. This is 50 hertz. Therefore Tp is equal to 2H upon D F0. So H is given 5 seconds. So 2 into H, D we have computed 0.01. So D into your nominal frequency is 50. So Tp actually 20 seconds, right? This is the power system time constant. Sorry. And Kp is equal to 1 upon D. So 1 upon 0.01. So it will be 100 hertz per unit megawatt, because reciprocal of this, so dimension will be reversed, right? So it is your 100 hertz per unit megawatt, that is your Kp, right? So these problems are very simple, you can easily do it. Now Another one is, this is example D, the fourth example, right? This is example D. Find the static frequency drop for the 1000 megawatt system. This you are described in example C. I mean, same data, whatever is here, example data, same data has been taken, right? Following a 1% your load increase. So we know steady state error delta FSS is equal to minus delta PL upon D plus 1 upon R, right? So it is given that delta PL, that is 1% change in load, means 1% means 0.01. So delta PL actually your 0.01. So minus 0.01. D is, we have computed 0.01 and it is 1 upon R, right? R is equal to your what you call 2, right? So in this case your R is equal to given 2 Hertz per unit megawatt. This R is taken from this previous example data. So R is given here 2, right? So that means minus 0.01 upon 0.01 plus half, because 1 upon R is 2. So that is minus 0.0196 Hertz. This is the answer. This is example D, a small example, right? Such that you will have no confusion when you will go through this recorded lecture throughout, right? Now example E, this is the last fifth example, right? Some more I will show you. A 1000 megawatt control area 1 is interconnected with a 5000 megawatt control area 2. That means area 1 PR1 rated capacity is 1000 megawatt and area 2 PR2 rated capacity is 5000 megawatt, right? The 1000 megawatt area, that means area 1, right, has the system parameters given below. That 1000 megawatt parameters are given below. R1 is given 2 Hertz per unit megawatt. Then D1 is given 0.01 per unit megawatt per Hertz, right? And delta PL1 is given 0.01 per unit megawatt. This is a step load disturbance. Now area 2 has the same R and D on 5000 megawatt base. So area 2 actually has same R and D value on 5000 megawatt base. Find the static your frequency drop. Then what is the frequency drop? Now as it is 5000 megawatt base, look, so find the static frequency drop, and whatever it was given, that was say 1000 megawatt base and area 2 is 5000. So D2 should be equal to 5 into D1, just straightforward you take. So it is 5 because it is your 5 times more actually, right? So 5 into D1 is 0.01, so 0.05 unit megawatt per Hertz, right? And R2 will be just R1 by 5, because here it is area 1 1000 megawatt, area 2 5000 megawatt, and you have to, area 2 has the same R&D on 5000 megawatt base. So R2 actually will be R1 by half, right? So if you look at that, your what you call the example C data, R is equal to, right, R is equal to, that is your, it is written no 2 Hertz per unit megawatt. So it is Hertz per megawatt, right? If you don't convert it to that, then it will be Hertz per megawatt, otherwise Hertz per unit megawatt, and it is 5 times more on this base. That's why R2 is divided by 5 times more. Don't multiply, you can look at the dimension and then you do it. So R1 is 2 Hertz, whatever is taken, right, and whatever is given here 2 Hertz per unit megawatt, so 2 by 5, so it is 0.4 Hertz per unit megawatt, right? And we know the steady state, your what we call frequency, this thing, delta FSS we know, delta PL1 actually minus your what you call A12 delta PL2 divided by D1 plus 1 upon R1 plus D2 plus 1 upon R2. Anyway, delta PL2 is 0, right, whatever it is, and delta PL1 value you put, and D1, D2, R1, R2, everything is known, right, and disturbance is only in area 1, that is your 0.01 per unit megawatt, only in area 1. Delta PL2 is 0. If we take A12 is equal to minus 1, it will become plus. Previously all these things derived, you will get minus 0.00326 Hertz. This is the steady state error in the frequency. So whenever you say the static frequency drop, means this is the steady state, this thing, right? That means your, if it is a 50 Hertz system, then system frequency will be F0 plus delta FSS, right? That means it will be 50 minus your 0.00326 Hertz, whatever it comes, that will be the system operating frequency, right? And this is your what you call that steady state error of the frequency. Now this 4-5 example, small one, you should go through very carefully, right? So once this is done, then what you can do is, now look at this, your what you call this diagram once again. Now suppose here only I will explain. Look, A12, going to the next page here. Suppose A12 is equal to, we know that A12 is equal to minus say PR1 by PR2, right? That we define as your what you call that area capacity ratio PR1 upon PR2, right? Now if your PR2 is suppose PR1 is fixed and PR2 is increasing, right? That means this value will go down, A12 will go down, right? So suppose something if you put that PR2 is equal to say alpha PR1, right? So minus sign is coming because of the direction of the type power flow, right? So that's why otherwise we call it the area capacity. Suppose PR2 is alpha PR1, then alpha will be actually your what you call PR2 by PR1, right? So if suppose for example PR1 area capacity say PR1 is equal to say, for example, say 100 megawatt. Now then PR2 will be then 100 into alpha. Now question is that if you go on increasing, suppose area capacity suppose is higher, you are go on increasing, then what will happen? This A12 value will actually your decrease, because alpha make your alpha is greater than 1, right? 1, 2, 3, 4. So that means your A12 it can be written as minus, and PR2 upon PR1 is equal to alpha, that means minus 1 upon alpha. So if alpha is greater than 1, go on increasing, then A12 value will decrease. That means in this diagram, when A12 value is decreasing, going on, I mean if you area capacity ratio of this area capacity of area 2 is increasing, that means this A12 value is decreasing, right? So if you go on increasing like this, I mean if you see theoretically, I'll tell you, then this whole system actually will have no effect on this system, right? Because this frequency deviation will be almost negligible, right? That means if it is much higher, then this side will act like an infinite your system, right? Infinite system. So that means if the area capacity ratio, area capacity of area 2 is much higher than this one, then this whole system can be taken as now we have considered a single machine infinite bar system. So that means, so not for this system, for composite system and other thing I cannot tell directly, but I have some ideas that if your this what you call this alpha value, if alpha actually greater than equal to 7.5 say for this system, that means if it is 100 megawatt, it is 7.5 times the 100 megawatt, right? At least greater than equal to, then you will find this frequency deviation is almost negligible. That means frequency operating frequency for this side compared to this one will remain constant. That means whole this system can be considered as a single machine, or what you call the way the system area 1 is connected with an infinite bus. So if you do so, then it will be something like this. Just hold on, I am showing you. So it will be something like this, that this is your system, like this is your system, this is U1, area 2 nothing will be there, this is your 1 upon R1, right, or 1 upon R, same thing. This is your 1 plus STG, right, and this one your 1 upon 1 plus STT, and this is your delta PG, this is plus, this is minus, delta PL, this is your Kp upon 1 plus STP, this is your delta F, and it is coming from here, and next this is delta F1. Say for example, I can put delta Pg1. Say this is delta E1, right? And this side is your tie line will be there. This is plus, and this side is your delta F2 is equal to 0 minus. I told you that because the area capacity is, but tie power will be there. This will be there. Tie line is there. So it is 2 pi T12 upon S, and here it will be there. Here it will be there. This side it will not be there. It is something like you have studied no single machine infinite bus. For power system analysis, what is infinite bus? Everything detail has been explained. So this is something like your infinite your system, that is we call infinite bus, right? And here that means here frequency is constant, F is constant, V is constant. So frequency is constant means delta F equal to 0, because this capacity is much higher than this one, at least 7.5 or more. This side if it is PR1, then this side will be 7.5 times PR1 or more. Then it can operate, it can act like an infinite bus, single machine infinite bus. So that's the input, that the frequency is constant, but this is tie line. This is tie line is there. That's why this tie line modeling will be coming here, right? So, and this is your what you call that delta F1, delta F2 is not there, but this is your what you call the tie line power flow. This is your tie line power flow, and if you want area control error from this area, it will come here, right? I am not showing this. So what you will do, this is an exercise for you, and I will appreciate if you can, when you will go through this, and if you can get the answer and let me know, then I will know that you have really understood this, right? Question is, you take U1 equal to 0, uncontrolled mode, right? What you have to do is, you have to find out steady state error of frequency and this tie power. Then you have to find out for uncontrolled mode delta F1 steady state is what, and delta P tie 1 2 steady state is what, right? These two you have to find out in terms of R1 and Kp, right, and delta PL. Other things will vanish anyway, right? This transient, this thing will have no effect as steady state. And of course, in terms of 2 pi T12 here, 2 pi T12 term is here also, right? Here it is little bit clumsy here. It is 2 pi T12 divided by S, this one, this block, right? So in terms of your whatever it comes, that in terms of 2 pi here, T12 is here, Kp is here, and R1 is here, so, and delta PL is there. So you have to find out what will be the delta FSS, a steady state value of frequency in the for such kind of system, and what is delta P tie 1 to SS for a step load change. For U1 is equal to 0. This is an exercise for you, right? So you will do this. Once all these things done, so little bit your what you call that conventional AGC or load frequency control rather, right? Everything is explained. So and numericals and other things are not very difficult one, and putting in state variable analysis, I hope everything I have told you. So next is that that little bit will show you that what is automatic generation control in this structured power system, deregulated market. Here no block diagram I will show, only some ideas will be given to you, such that you will have some ideas what actually going on, right? So no block diagram representation, not much calculation, just some concept and little bit of thinking that how you can go for deregulation for such kind of thing. So now that is actually what we call automatic generation control in a restructured power system. Restructure means in the deregulated market. So before moving to that, suppose earlier what happened actually all over the world, that one utility used to own the three things, that is generation, transmission and distribution. Suppose you have your own electricity company, then you have your own generation, transmission and distribution companies, right? And that means it is actually you yourself controlling everything, that your generation, transmission and distribution. Now under the restructured system, it is not like that. So in that case, suppose someone may have generation companies. For example, suppose somebody called A, he has his own generation companies, right? And he is generating power, but he has to sell power. And somebody has somebody has your say B, called B, he has say he or she has just transmission companies, right, and somebody called C, he or she suppose has distribution companies, right. So ultimately power distribution companies has to buy power from the generation companies. Suppose several generation companies are there, and power wheeling will take place to the transmission network, but transmission company owned by B, generation company owned by A, and distribution company owned by C. So completely three different entities, right. So in that case what will happen, that earlier if you have your own companies, generation, transmission and distribution, so there is no change in the infrastructure, it will remain as it is, right. Even your what you call that even if you break it, generation, transmission and distribution, ultimately it is owned by you. But if somebody has the distribution part totally, and he is responsible, he or she is responsible for your what you call for selling power to the distribution side, then he has to buy power from the generation companies through your through the transmission line, but transmission company is different, right. So because of this thing, I think power system concept is becoming very complicated but competitive also. That means suppose some 10 or 12 generation companies are there, and it is a competitive market, and you have a distribution companies, and you want to buy power from the generation companies. So many suppose today when I am recording here, it is now 12:15. At this time, suppose 5 generation companies are selling power to distribution companies, right, and distribution company will see from where I will get the cheapest power. So accordingly they can contact with the different generation companies. So market is competitive, and therefore your what you call that expecting that because of this competition, that your price of electricity may go down, because competition has been your this concept has been introduced. Actually this restructuring of power system or this thing, from where it has actually first generated this concept. This concept, I was listening one lecture from one professor from abroad. So he actually visited that country in South America. So whatever I have learned from him, after reading, he said this restructuring in power system actually concept came to the Chile first, right. Actually they were thinking this kind of restructuring. That was many years back, that in his lecture I was listening to him when he was giving lecture in our department few years back. But today that your what you call this concept of restructuring has come to in effect. So therefore that restructured power system, the engineering, whatever I told you, the engineering aspect of planning and operation have to be reformulated, although essential ideas remain the same. Generation, transmission, distribution concept will remain same, only competition has been introduced, right. So the electric power business at present is largely in the hands of vertically integrated utilities. Vertically integrated utilities means you have generation, transmission, distribution, everything together. You are the owner of everything. That is we call vertically integrated utilities, which own generation, transmission and distribution that supply power to the customer at your regulated rates, right. Now such a configuration is shown conceptually in figure 1. I will show you, in which the large rectangular box denotes a vertical integrated utility thing, right. Therefore this is a big box I have given. This is transmission side. These are all generation. Right. These are all generation. This is then this particular area. It is, I showed you that it is connected to some other areas, tie lines. These are tie lines, and transmission power is coming directly to the distribution, right, and then power is being distributed. And IPP is independent power producer. That means private parties also, some private parties which are generating power at high voltage level directly can be connected to the transmission system, and some parties which are generating power at low voltage level may be connected to the distribution side. This are IPP is independent power producer. Here also IPP is there, like generation companies. This IPP also generating power here, right, here also. So right, this is actually vertically integrated utility structure. Everything is owned by you. With that, some private independent power producers, some private parties are also connected with that. Thank you very much. We will be back.